on Friday. And what we're talking about in lecture is the addition to alkenes and the idea of taking something that is less stable, a pi bond, and turning it into single bonds. And the motivation for many of these reactions is to do exactly that, is to get to a more stable product. And in this example, you can see now that Br2, as we described on Friday, is a pretty weak bond. You'll see a lot of reactions coming up in which bromine is the reagent, and the motivation here is to get rid of that bromine molecule and turn it into something else. So when you're doing your E1 reaction this week, which I think is right now, 4-methylcyclohexene, one of your tests at the end to see if you did this right will be to add some bromine to it. And bromine is a deep orange color. When you dissolve it in organic solvents, it will mix with the organic material that you made, and you'll do a test. You'll do a control with the starter material, which should not change color because it's not an alkene, and then you'll do the product. And if your product is an alkene, the bromine color will disappear. It will go colorless, and that's a good thing. So what's happening here is the addition of the Br2 molecule to the alkene. And this is an example, not so much of any interest synthetically. We don't really use these things a little bit maybe in chapter 10. But it's showing you now stereochemical issues. It's showing you the fact that this is an anti-stereochemical outcome. This is not syn like we did for the hydrogenations and the hydroborations. So the fact is you get these two products. You don't get the other isomers where they're both wedges or both dashes. They just do not form. That tells you a lot about the mechanism. All right? We're going to see it's a stepwise mechanism. It's not syn addition. It's going to be stepwise and through a carbocation type species. And we made an argument on Friday about the fact that Br2 isn't polar until you make it polar. And basically you put it in the presence of some polar material, you get repulsion, and you end up with a polar molecule. So this little dipole down here is important. That's why the pi bond will go after one end of the Br2 molecule and force the other one to break off, right? So we're inducing a dipole temporarily to make this thing work. And if you do this, you get addition products. The thermodynamics behind this, obviously the bromine molecule is weak, so you want to break it, and we're going to form possibly a carbocation. So the reason this is here is to question what's happening, to make sure that you understand the consequences of the stereochemical issues in these types of reactions. Obviously, they're very important. Now, why can't it be a carbocation? What would a carbocation give me if the Br minus then added to that carbocation, potentially? It could give you racemic mixtures. Yes, it could give you products in which both the bromines are up or both the bromines are down, and that does not happen. So the idea now is that this is not happening. We're not getting a simple carbocation, and there's more to it, because that would give you products of both syn addition and anti-addition, and we don't get the syn addition products. So these little pieces of information, again, you may never see this reaction again in your lives unless you take a standardized test, but you will start to think like a scientist and start to question. You'll start to look at an outcome and say, all right, I know enough information from this reaction or this experiment to be able to work out what happened. This is similar to if I asked you, how do you speed up an SN2? What do you do to speed up an SN2? Add more nucleophile, right? Or the rate equations will change depending upon what's involved in the rate determining step. This type of information is really key for this sort of critical thinking idea to solve problems. So this is the argument. We get something that looks like the mercurinium ion from the mercuration reaction we did last week. You get a three-membered ring called a bromonium ion. And this is a little bit weird. We don't think, three-membered rings are usually unstable. That's why it doesn't stay around. It will do something else. But bromine is quite large. And so bromine can sort of span both carbons and bond to both carbons at once. Plus, it's got loads of lone pairs. So it's got everything you need to do this. It lands itself on top of the alkene. The mechanism looks like this. Yes, we're attacking from the pi bond to the delta positive bromine. The bromine then is compensating by pushing a pair of its electrons back, because it has them, just like mercury had. And the Br here behaves like a leaving group and disappears. So we have this nice delivery of Br on top of the alkene. And we don't have to worry about the attack from the top. Number one, this thing is blocking the top. And number two, like in an SN2 reaction, the Br minus has to come from the opposite direction from which the leaving group is breaking off. Now be very careful. I'm going to say that again. This is behaving as a leaving group, yes. But is it leaving completely? No, because one bond is still attached. But you would still say that's a leaving group breaking off, even though it would still be attached. At the end of this, we end up with the stereochemistry that is observed. And again, we keep saying this as we hit new chapters. We isolate this stuff, we work out what it is, and then we work backwards. We knew what we started with, we know what we get, we then work out the mechanism. The mechanism is not sort of thought of first. So we know that we get these trans isomers. The argument now is they come about because of this bromonium ion, and that gives us a nice outcome. I keep using the word organization. And I've got time this afternoon after 2 o'clock if you want to come in before 4 and do some organizing, if not tomorrow, because chapter 9 starts to get very big. However, if you take your time with it and you organize yourself and you think about the consequences of syn addition, of trans addition, anti-addition, it isn't that bad. It's just more study. We are trying to sort of show commonalities now. If you understood this argument for the mercurinium ion a few days ago, you should be able to understand this for the bromonium ion. They both had a lone pair to compensate for picking up the pi bond, And these are not stable species per se, but they will form to help stabilize the system overall. But I want to point this out. Bromine wants its electron pair back. What is the electronegativity of Br? 2.8. What about carbon? 2.5, right? What if you make bromine positive? Because it had to share a pair of electrons to become positive. Is it now more electronegative than it was or less electronegative? Think about it. It wants that lone pair back, right? It's much more electronegative than it used to be. So the argument is, even though we draw the positive charge on the Br as a formal charge, it is the carbons that are delta positive. So as you think about the mechanism for this type of reaction, keep an eye on the fact that it is the carbons next to the positive atom that are really bearing the positive charge. And that will have something to say in a few minutes when we talk about stereochemistry and regiochemistry, when we have a tertiary versus a secondary system, and we get different outcomes. So these are similar. As you practice these things, make sure you see the similarity there. And then we have to deal with the stereochemistry. And we have to deal with the fact that this reaction only gives certain products. And we'll take our time with this, take a few minutes over it. We'll do it in recitation. I can do it in the office hours easily enough. We are now starting with alkenes that have prochiral carbons. I've got methyl group here, I've got hydrogen here, I've got the other end of the molecule here, and I'm adding a bromine. So in this case, I'm making two different chiral centers. So potentially I could get 4 isomers. The fact is you only get 2 of them. That's what's telling you about the mechanism. That's where the bromonium ion came from, because you only get the trans products, you don't get the syn products. Well, in this case, with cis-2-butene, I get these two. What's the relationship between those two, you think? Give me a word. They are enantiomers, exactly, right? So they are the plus-minus mixture. That's what happens when you add to cis-2-butene. That's the outcome. Well, when you add to trans-2-butene, you don't get that same outcome. So again, the identity of the starter material is having something to say about the identity of the product. So what was the word we used for that? Not selectivity. Specificity, right? Specificity, stereospecificity. The starter material identity, be it cis or trans, is having an effect on the outcome of the reaction in terms of its stereocenters. So again, we played about for a while in chapter 5 with the idea of drawing these things as wedge dash, doing some rotations about bonds. The fact is, in this example, with the trans isomer, you get the meso outcome. Now, this is only going to be meso because these two guys are the same at each end. If you start to change that and you start to make this unsymmetrical, you'll get enantiomers, right? Because you're making molecules that are not meso. So this is just an old experiment. It's a classic experiment to show how these things are working, but also to test whether you understand the consequences of stereochemistry and inducing stereochemistry by adding things to alkenes. And that's just something I'm very keen on between now and the final. I want to make sure going into the second semester that people have got these ideas worked out, right? Because second semester is that much more difficult. Michaela. It would still be the same compound. Don't forget that if you have a meso system, you don't get 4 isomers because 2 of them are the same. Yeah? 2 of them are the same. They will be superimposable mirror images. So therefore, you don't get 4 isomers here. You get only 3. And the point of the slide is that you get a different outcome depending upon whether you start with the cis or the trans alkene. That's important. Now, there's a lot of stuff on my website with this for this idea in the course packs and practice things to do. If you can handle this stuff, you should be able to get an A in the class, and you should be able to get through 3720, no problem, right? So look at it that way. So I bought this from an old book that we used to use. I like this because it shows you a different look at that reaction. On the top of the slide, we have the Z2-butene, the cis molecule, and we are adding the Br2 to it. Now, if you're totally lost on this, we need to talk. If you are starting to get a grasp of these things, write this out. Try it. You know for a fact that this goes through a bromonium ion. So what you would draw first is some species that has Br at the top maybe, looking like that, the alkene is gone, and a positive charge right there. That's the intermediate. And if that's the case, look where the 2 methyl groups are. They haven't had a chance to reorganize. They are pointing in the same direction. That's key. Now, when you bring in the next nucleophile, the Br-, it attacks from the bottom. And I do that, and I push this up, and I get my anti-product. Now look at that. There's my anti-product right there. Look at the relationship of the 2 methyl groups. They haven't changed. Where they started on the same side of the alkene, they end up in the same side of the product. That's the important issue here. And that tells you it was through a 3-membered ring and it wasn't through a carbocation. Because if you have a carbocation with a single bond, you can just rotate around it, right? And that would lose the stereochemical integrity of these products. So again, have a go at this. I will do this in recitation. It's kind of fun to see where this comes from. You will see that attack on the left will give you this guy here, and attack on the other carbon would give you this guy here. And that's where the enantiomers come from, that process. Now, if I put the bromine on the top, I'll get outcomes. If I put the bromine underneath, I'll get outcomes. Try this one. If you can do this, you should be getting an A in the class. You'll find that the outcomes are the same regardless whether you attack from top or bottom. You get the same two enantiomers for those products. It's a really nice test of whether you're really getting the idea of stereochemistry. So the other isomer was the trans isomer, and the whole point of this is the outcome is helping us prove the mechanism. We have two methyl groups on opposite sides of the alkene here to constitute the trans isomer, and if this truly is a reaction in which we have a three-membered ring and we're unable to rotate around that cycle, then the methyl group should end up on the opposite sides of the molecule in the product, and they do. So again, draw the bromonium here, put the bromine on top after it's added, and you have a positive charge there, and you have the three-membered ring like so. And then the Br minus has to come in from the opposite side. So it comes in from underneath, opens this thing up, that gives me this product, and if you come in from the other side over here, you get this product. Now, go back to chapter 5, think about the rotations we had to do to decide if these things were meso or enantiomers or diastereomers or whatever. It turns out that these two, in fact, are meso. So one stereocenter is R, the other stereocenter is S. They cancel out, and what's the optical rotation? 0. Okay? So this is kind of getting interesting, kind of getting fun. Again, my thoughts on the next two exams, I want people to be able to handle this stuff to go into the next term. 3719, get through it. Not necessarily going to set you up for 3720, you have to do well. Any questions? How was Halloween? Obviously horrible. I missed it completely, it was great. All right, that's a tricky one, no doubt. But if you want to be challenged, there you go. Think about those problems. Now, the whole point of doing these reactions again is not to necessarily give you a collection of reactions that are that useful. These aren't that useful. It's to think about the consequences and the sort of critical thinking that you have to do to be able to analyze the situations, the products, and then work out exactly what happened. There is an allied sort of parallel reaction called a bromohydrin type of formation, in which instead of just adding Br2, we put Br2 in with water. Now this one is useful. This one is going to be very useful for making oxygen rings. If you were able to have the bromonium ion in the presence of something other than Br minus, that other thing could behave as a nucleophile, and it could undergo addition just like the Br minus did and give us that. And that's a compound in which one Br, or the Br is added at one carbon, and the OH group is added at the second carbon. These will be very useful in the near future. So how you run this technically is interesting, because if you're adding Br2 in this same reaction, because the conditions are exactly that, you add Br2 with H2O, and what you're trying to do now is avoid the Br minus behaving as a nucleophile. You want the water to behave as a nucleophile to get involved to give these useful products. So how do you do that technically in the lab? How do you, say again? Add a lot of water, it's as simple as that. You add a lot of water, because if you add a lot of water, you swamp out the nucleophilic character of the Br minus, and the water gets involved instead and can give you that outcome. Go ahead. Not there yet. Next slide. The bromonium ion is the intermediate species here. It's a positive species that needs some help. So we're going to attack things with nucleophiles. In this case, we're swamping out the Br minus that got involved in the last reaction. In the previous couple of reactions, we just had Br2 in some inert solvent that does not get involved. So what we have left over in the second step is Br minus. That can now get involved. We want to try and get rid of that or sort of minimize its possible chances of reacting here by adding a lot of water as the solvent, swamping it out, and therefore this gets involved. So the mechanism will be very similar. And again, organization is key here. Don't learn this thing twice. It's the same mechanism. You just need to learn that the conditions here are modified, and so water now gets involved instead of Br minus. Again, first step, just like the addition of Br2 to give yourself the three-membered ring, the bromonium ion, that thing is reactive. It's the delta positive carbons that are now interested or involved in this because they're delta positive, and we have a nucleophile water that goes after one of those carbons, and we open this cycle up again to give this, followed by this. That's a proton transfer, and that gives me the product. All right, so that's a useful reaction. Now it's a very, very useful reaction to go someplace else in the near future. But again, it exemplifies, look at the outcome. The outcome is the trans stereochemistry on that cycle. It's not the cis stereochemistry, and therefore that must be a three-membered ring intermediate. Okay, I've got, I don't know, 4 or 5 reactions left in this chapter, and then we're into 10. So it's getting quite busy. This is that question that Ashley asked. What happens when you have a non-symmetrical alkene? Well, then it gets more complicated, obviously. In this system, we're going to make a bromonium ion here, and then it gets attacked. And it could get attacked at this end, or it could get attacked at that end. Now, when we did this with the mercury, it seemed like the nucleophile went for the more crowded carbon. And that should be consistent here. In fact, it does exactly the same thing. If you add the Br2 to this alkene, and you make the bromonium ion, this nucleophile now has a choice. If it went here, you might think, all right, that's less crowded, and maybe it does like an SN2 reaction. Or if it goes here, that would be like an SN1 reaction. Now, you've got to be careful here because the whole argument is about this type of transition state. Where in this molecule do you want that positive charge? Again, don't forget, you have a bromine that is inherently more electronegative than carbon. So the bonds between bromine and carbon are polarized towards the bromine. If you make bromine positive, because you took one of its lone pairs, you make it more electronegative. So there is a significant dipole between these bonds, between the bromine and the adjacent carbon. So both of these carbons here will be significantly positive. Where would you rather have the positive charge? On the left or the right? On the left because it's more substituted, it's tertiary, right? Also, if you look at what's happening here, if that bromine is pulling its electrons back away from the carbon next door, that will have something to say about the hybridization carbon, the hybridization of the carbon. So you think about a regular tertiary carbon, it's sp3, right? That's why everything's blocked, you can't get there. But if this bond is starting to break above this carbon, what's going to happen to these pieces here? They'll flatten out like this. They won't go completely flat because it's not a full carbocation, but they will start to flatten out, so they'll get out of the way. They're not going to be such a problem like they would be for tertiary SN2. So that's the argument here. The water can get here because it's accessible, and that carbon there is quite positive because it's tertiary and can handle the positive charge better than this carbon here. So this now is regiochemistry, where the chemistry is happening. And to a degree, it's obviously stereochemistry because we're getting an anti-product. So everything's coming in here to sort of play a role. So be very careful here. Take your time, organize yourself, study sheets, whatever you want to call them, look at my mechanisms online, make sure we're happy. Go ahead.
Can we get to a case where alkenes attack water, or is that they have
That's kind of counterintuitive, isn't it? They're not that acidic. And also water's nucleophilic and the alkene is nucleophilic. So they would probably repel. All right. So we're moving along. We've got some problems here to practice. You will have quizzes now each week except the week with Veterans Day because Veterans Day is on a Wednesday, so we can't quiz on the Wednesday. But every other week now we'll have an in-class quiz to make sure we're keeping up with this. And that's the whole point of this, is to just get you keeping up with it or else you get lost. What's going to happen here? I have Br2 in CCl4. Am I going to get a bromohydrin or am I going to get a dibromide? Dibromide, right? There's no extra solvent that will help out. CCl4 is inert, it doesn't do anything, and so it doesn't get involved. So we expect to see addition of bromine across the alkene in an anti-fashion to give the trans outcome. In this case, because we have a chiral center involved, chiral centers, we're looking at racemic mixture. Can I use the squiggles here? The squiggles have been a bit controversial. No, why can't I squiggle here? They have to be set stereochemistry, right? If you draw both squiggles here, you're saying that you also get two wedges and two dashes, and that does not happen here. So be careful with your squiggles. Do not over squiggle. I'm going to add Br2 and I'm going to add water. What am I going to get? The addition of Br2 or the addition of BROH? BROH, because my water's involved now. Simple enough. And if we think about where the water's going to go, is it going to go on the left or the right, do you think? On the left because it's more substituted. So there are some problems in the homework and on the online stuff that I've done, the course pack, that have exactly this. And hopefully there's an explanation in there that you can see where it comes from. It's really starting to get quite busy. Racemic, how many stereocenters in that molecule? How many stereocenters in that product? How many stereocenters in that product? One. Okay? Because this one has got two methyl groups, so it can't be. Now, down at the bottom, adding as you will in lab this week, be very careful with bromine. Be very careful. Do not get it on yourself. Do not get it on your clothes. Do not get it on me. It is very, very dangerous stuff. Be very careful with it. You add this dropwise, maybe, to this alkene. Color disappears because it's reacting, and we end up with products. So we're getting syn addition or trans addition? Trans anti-addition. That should give us this. It doesn't matter where you start. Put the bromine on one and the other one goes on the opposite, and it's racemic because we're generating stereocenters. Again, I can't use squiggles here because that would be incorrect. That would be telling that I had all of the isomers where I don't. So we've covered quite a bit. We've covered Markovnikov addition through carbocations. We've covered additions through sort of pseudo-carbocations, like this guy and the mercurinium species. We've covered syn additions. We've covered anti-additions so far. We've sort of done a lot here. So I always take a time out here in class to mention some things that people should be thinking about now, right? November is classically start time for people who want to take MCATs, PCATs, GREs, and think about applications for the following year. For you lot, this will be next year. And I always put this in here to wake people up and make them realize that you will need letter of recommendation, right? I've never met anybody called Billy Bob. I'm sure they exist, but it just sounds like a cool name, right? So Billy Bob wants to be a pharmacist, and that's just an example. And he's got the GPA, and everybody works at Giant Eagle, right? So, you know, they've all got the experience. And then he comes into the organic sequence, and then he wants to take biochem, and you're starting to get sort of bit more of a clue about how this all works. And you want to learn, you're learning the subject matter, and you should be learning about people, and you should be getting people on your side. Maybe we've got to take the PCAT, the MCAT, the GRE, the OAT, all these horrible tests that people have to take for entry. That's coming up in your future. Great, well done. You've got to get letter recommendation, and this is where things start to fall apart, right? Because people don't talk. They're too busy texting each other. They don't actually talk to each other. Now, in this class, I know about half the names so far, maybe 2/3. Some of you have spoken to me, some of you haven't. But can all of you list 3 professionals that you know from YSU that would be happy to write you a letter recommendation? Half of you can't. Most of you cannot, right? And this includes going for a job in the future. If you're looking for a job, which most of us are, or would be, you will need people to speak for you. Right? I do a lot of this stuff, write letter recommendation, phone calls with employers. What's this person like? Well, this person has a 3.8 GPA, never says a word. Don't know them. And people get upset when you say, no, I won't write your letter recommendation because I don't know who you are. So just a piece of advice, go start talking to people, thinking about next year. Most of you are sophomores/juniors. Next year is going to be crucial, so get on this. Make sure people know who you are. If people come into my office and say, I had you for organic, I got a B, can you write me a letter recommendation? If I don't know who you are, no. And it's the same for people like Gary Walker, it's the same for Chet Cooper, whoever else is in biology over there. Make sure you know these people. All right, back to the chemistry. We have done a lot of different additions. It is up to you to stay organized here. We've done syn additions. You can categorize these things quite easily. Syn additions tell you it's a concerted process. We have the addition of boron and the addition of hydrogen. They both happen in a syn fashion. How do we know this? We get the products and we isolate them, we look at them, and techniques you'll see next semester, but we know exactly what they look like, so we can infer backwards and see how that happened. We can work out the mechanism. So as you're organizing yourselves, we have done syn additions. Typically they are concerted. We've also done some anti-additions. And these anti-additions are now showing you that it probably wasn't a carbocation, a pure carbocation, because that would give you a scramble. That would give you all the isomers where you don't get all the isomers. So that's an example of how that happened. What we'll do now to finish this off is a bunch of oxidations. Oxidation is an incredibly important idea in organic chemistry and biochemistry, so we're going to have to get comfortable between now and the end of next term with what constitutes oxidation and how carbon deals with it, how carbon deals with reagents that want to oxidize. So we're going to see now a reaction which is a syn addition. To make an epoxide, these species show up next term. They're vital for doing synthesis to be able to make all sorts of materials. So we're going to deliver from this guy an oxygen atom onto the alkene. We're going to get a syn addition. You can see, you probably can see this anyway. If you try and make a model of this thing, you try and make the trans isomer, you'll break your model kit, right? It'll just twist up and snap. So the only thing you can actually do is put the oxygen on one side. And in a very useful second step, we'll add acid to this thing. By now, people who are looking to get A's and B's should be able to think of mechanisms for these things. What do you think will happen first in the presence of acid? Protonate the O. Why do you think you'll protonate the O? Make it a better leaving group. And then the second OH comes in from the water and away we go. Why do we get the trans outcome? The same reason we got the trans outcome up there. Things will start to fall into place if you have kept up. So we're going to talk about this concept of dihydroxylation. Carbohydrates contain diols. You've got to be able to introduce them to make new materials and new pharmaceuticals. So we have methods to do this. We're going to see synthesis of things like ethylene glycol, very useful as antifreezes, everybody knows, but in a more general sense, putting that OH group next to each other, those OH groups next to each other is really, really important. So we'll see now that addition of something called a peroxy acid. If you think about what this is, if you were to draw a carboxylic acid I think everybody's happy now with the abbreviation RCH2OH, because we learnt the functional groups. Well, we've added this extra oxygen. You'll see in a second that that extra oxygen gives you an OO bond. And last week that was unstable in peroxides. Well, it should be still unstable this week. Just because it's November, it's still going to be unstable. So we'll want to break that OO bond. So you'll see this reagent a lot of times. If you see the O3 in that molecule, it's going to want to break apart. And what it does is it delivers the extra oxygen onto the alkene, and it makes an epoxide. Epoxides, again, very useful. And then what we'll do is open this thing up in a mechanism that you should be able to do preemptively now, if you're doing well here, and that gives us the transdiol. So again, we know what this is, we can work backwards, and that tells you a lot about the mechanism. I would say from now on, the mechanisms that we do, apart from ozonolysis, which is quite different, all the mechanisms we do to the end of term should be logical to you. There shouldn't be any surprises from now on. Well, this one, I think Tyler likes this one because it's just horrible. It's got 4 arrows in it, all right? And it's showing you the concerted delivery of the extra oxygen to the carbons to make an epoxide. So those epoxides, just like the bromonium ion, just like the mercurinium ion that we saw already, they will be unstable, they'll want to react later on. So what's happening here is that the motivation for the process, that's probably the first thing we should look at. We have oxygen next to oxygen. Like we had Br2 unstable, like we had hydrogen peroxide, OHOH, unstable, this is unstable again, right? You've got to be careful with this stuff. So what's going to happen here is an attempt by this molecule to get rid of one of those oxygens and break that bond. That is the motivation or the driving force for the reaction, is to get rid of one of those OO bonds. The way this happens, the most logical way for this to happen, is to go through a process like this, a transition state like that. Now that's pretty rough, right? That's probably the trickiest transition state we've seen so far. Probably the one of the worst you'll see. The arrows to describe this are, let's think of it this way. That arrow is going after the oxygen. This arrow is doing what bromine did. It's delivering one of its lone pairs back to the carbons to compensate for a positive charge being formed. So we're doing a very similar reaction to what we did with bromine. Double bond goes after the atom delivers one of its lone pairs back to make a cycle, and a leaving group breaks off. So the 2 key arrows here are the ones I've labeled, this one here and this one here. The other arrows are just to compensate. Okay? The other arrows are just to get rid of a sensible molecule. This is now breaking off. What is this behaving as right here? What's that species behaving as? It's a leaving group, exactly. That's a leaving group. It's taking a pair of electrons with it. And to balance this whole thing out, what type of step is this? Proton transfer, that's all it is. So because of the nature of this thing and the ability to form a 5-membered ring transition state, this molecule can do everything at once, which seems like it's complicated, but actually simplifies the whole process. So here is one of the bonds forming, this arrow. This is the other key bond forming, this arrow. This also shows the pi bond breaking. And then all of this other stuff over here, this is really just extraneous. I'd like you to know how to do it, of course, but that's really not that important for the formation of the epoxide. How many steps in that process? 1. Okay. How many bumps on your reaction profile? Just the 1. Okay, so don't forget about those things. We should be able to draw them. So there's the argument for the actually how that happens. Obviously more to come in recitation. Practice these things. We've got some examples to show you and get a good grip of it. Now, this is why they're useful, down at the bottom. Look at this thing. We have a weak base, we have a strong acid. We're dealing now with the epoxide reacting with H3O+. The H3O+, what's its pKa approximately? Negative 1.7. So it can protonate things like epoxides quite easily. That will give us this thing. This should be starting to look familiar. It looks a lot like H3O+. It looks a lot like some of the systems we saw in the SN1 and the E1 reactions. You've protonated the equivalent of an alcohol. It doesn't look like an alcohol, but it's very similar. So this whole thing now is a good leaving group. But again, it's going to break, but it's not going to break off because it's bonded twice. That's what's different to the earlier systems. So why is this water molecule attacking from underneath? You've got some steric problems at the top, and also the orbital you want to deliver the charge into, or the lone pair into, is underneath. It's exactly the same or very similar to the SN2 reaction. If it were attacking from elsewhere, it would have problems. Why is this such a good leaving group? We have seen these things before, and this is the whole point towards the end of the term. put it into practice. Make it, apply the stuff. Why is that a good leaving group? Polarized. What's it trying to do? What's the oxygen trying to do? It must have been a pretty good Halloween by the looks of it. You lot are dead. The oxygen wants its lone pair back. That's why it's able to do this. If you make an oxygen positive, you make it really electronegative. It wants that pair back. That's why it's able to do this. Also, the fact that this is a strained ring and wants to break open. So the nucleophile doesn't have to be very strong here. Comes in from underneath, pops that ring open, and we end up with this. That's not quite the product because it has an extra proton. And on quizzes, this is where the A's become B's and the B's become C's. Those little details make a difference. They really do. So please try to put as much in as you can when you do the quizzes. Water comes over here. Where have I got water from? I used it up over here. Why have I got another water around? It's a solvent, most likely. It's a solvent, so there's lots of it, so we can do that no problem. And we end up with a diol. And that diol happens to be the trans isomer now. And we don't get the cis. So the argument now is that this is anti-dihydroxylation through steps. In this case, we're going to make the epoxide first. That is a syn addition, followed by an anti-ring opening. Everything's starting to come together. We're using the same sort of, different words in the same setup here. Tricky stuff. Anybody? Joe? You all right? All right. Fair enough. Moving along. The reagents we use for these reactions are somewhat, you've got to be careful with these things. Peroxyacetic acid is not particularly friendly. It has this OO bond which wants to break, just like H2O2. This is useful if you want to do reactions in water, if your materials are soluble in water, or very polar organic solvents. This one, you will grow to love. MCPBA, metachloroproxybenzoic acid. Do not worry about the name right now. In fact, you do not worry about any of this material over here because it does nothing. It just turns out to be a byproduct from a different process where the people who make this stuff sell the isomer they don't want, and we turn it into MCPBA and it becomes a useful reagent. So that chlorine is not there for any purpose that we are interested in. It's just an artifact of an industrial process that they sell the byproduct from to make money. What you are interested in is this. There's the business part of the molecule. Okay? It's exactly the same as the business part over there, so they do the same reaction. You see either of these guys, they will do epoxidation by delivering that extra oxygen to the double bond to make a three-membered ring. And the book, which I hope we're still reading, is very good at sort of summarizing these things. If you put these three species next to each other that we have seen over the past week, the epoxide now, which has been protonated and positive, the bromonium ion, which is inherently positive after the first step, and the mercurinium ion likewise is positive, they're all three-membered rings. They all want to break open. That's why in the second step, a nucleophile comes in quite easily, pops this thing open, and we get trans products. So as you study these things, make sure you see that. Don't see them as separate species, really. They all do the same type of thing, and it's quite logical. Okay, Colleen? Good. Joe? It's two. Yeah. It had a lone pair, and it's used its lone pair to compensate for forming you don't want to form a positive charge on the carbon if you can help it. So it's used its lone pair to compensate for that. So it doesn't have a lone pair there. I believe so. Actually. So if you have a choice of, this is more of a sort of a formal thing for writing exams. If you are showing two different processes, I want to see two different drawings, right? People have always get into this bad habit of, okay, this molecule rearranges in this direction, this direction, and this direction. And I don't want to write them all out, so I'm just going to put 7 arrows on the one picture, and hopefully Norris can read it. No, don't assume that. If this molecule here goes this way, draw it out. If it goes, a separate molecule goes this direction, draw it out. Keep it as simple as possible to make my life as simple as possible, because that's what it's all about. Do it twice, yeah. Okay? It's getting good. Now, to complement that type of reaction, we need a syn dihydroxylation. This may mean nothing to you, but I think I have a picture coming up. Maybe I didn't put it in this year. Maybe I've already shown it to you. Why do we need diols in molecules? Well, carbohydrates contain diols. You need to make carbohydrates to be able to do glycobiology, to be able to probe how cells and organisms use carbohydrates to be able to do biosynthesis and metabolism. So organic synthesis drives that by having methods to be able to introduce these types of structures. What we'll do now is the opposite. In the last reaction, don't forget we ended up with the trans isomer. You want to do it that way. Context as well. You're about to get into this situation where we will ask you to make molecules from scratch. They might be 2 or 3 or 4 or 5 steps away. You're given a starting material, you're given a product, go to it, right? That's not easy at all, especially if you haven't learned the reagents. So keep an eye on that. That was a trans outcome. Now I'm going to deal with the cis outcome. And the way we do this is not particularly nice. This stuff is quite toxic. I'll show you in a second that it's now catalytic, so you don't have to use a full equivalent of this stuff. But we do an addition. And that addition with OSO4 gives a species like this. It's a cycloaddition. It's the first example I think we've seen of a cycloaddition, where 2 pieces come together on an alkene and they give you a cyclic outcome. Well, all right, we've all taken general chemistry. We've all passed it, I hope. What about that osmium? Electron poor or electron rich? Let's just guess. Huh? Say that again. Look what it's bonded to. Use your scientific knowledge that you have gathered over the past 4 years to look at that molecule and tell me if that oxygen is osmium is electron poor or electron rich. Cool. It is attached to all these oxygens. Okay? And you will see that in a general sense as we head into the second term. Organic chemists will use metal oxides to do oxidations. Biology, you will use metal oxides to do oxidations. That class I taught in the spring, it was all about iron, right? Iron 2, iron 3, iron 4. Oxides, oxidizing things in biology. So we've got to get comfortable with this. Sorry, just coughing to wake people up. Don't mess with me, boy. We have osmium wanting electrons, right? So if osmium picks up electrons, does it get oxidized or reduced? Do you remember this? If you pick up electrons, is that an oxidation or a reduction? It's a reduction. Yeah? Picking up electrons is reduction. Giving away electrons is oxidation. So we've got to now think about why on earth this material would want to get involved in this type of reaction. That osmium wants some electron density back. Because in its production, to give OSO4, it had to give up a lot of electron density to the oxygens. Well, that is good for organic chemists because now these materials will react together using the alkene as a method to do that. The alkene really isn't important to the osmium. It's just there to be able to get to a system in which, yes, the osmium is more stable. So if you had to give me an oxidation state for that osmium, what is it? General chemistry was so long ago. How many bonds does this osmium have in that molecule? 8. And it's bonded to more electronegative elements. So give me an idea of an oxidation state. Plus 8, thank you. All right. Look at the product. What's the oxidation state over here? Plus 6. It has been reduced. It has been reduced. And that whole thing there is the driving force for this reaction. So how this works is osmium is going to be an electron sink. It's going to absorb electron density. And that happens through the pi bond going after one oxygen at the top. The osmium is able to absorb some electron density, and then this bond is going to form over here to give us this. Now, how do we know this is a concerted process? What clue is there in that product that tells you this is concerted? Syn addition. It's a syn outcome, right? And that's typically going to be a product or a system in which you have a concerted process. So make a note of that. This is a concerted process to give this syn osmate ester. Don't worry about the word osmate ester just yet. That will come later. But this thing now it's almost there. It has delivered 2 oxygens onto the carbons, and you now have a cis dioxygenated species. So the way we run this is to then take the product there, mix it up with some water and some base, and you end up with a diol. Now, we've got enough to worry about this semester. We will do mechanisms like this ad infinitum, ad nauseum next semester. So I'm not going to ask you to draw me a mechanism for that process. Just make a note of that. Certainly the first part, but not the second part. The second part is more like 3720 material. So what's happening here essentially is this bond gets broken, and we end up with a diol. How do I know this bond doesn't get broken? Well, what's the clue? How do I know that bond doesn't get broken? Not because I tell you it doesn't get broken, but as a scientist / engineer, you have evidence to prove things. How do you know that's not getting broken? Stereochemistry is the same in the product. Yeah, it's retained. It's not broken. So this is going to happen here. The logic behind this is fairly simple. Where's the most positive part in that molecule? The osmium. So if I have, let's say, hydroxide or something like that in these bases, in these mixtures, where's that going to attack? Where's the nucleophile going to attack? The osmium. The osmium, then this thing will break off, we'll end up with the protonation step, and that's it. That's all there is to it. But we'll leave that until next term. So we should be starting to see patterns now. We're making cis diols. They're very useful. And one of the big advantages, or big advances, I should say, in this type of reaction is the use of catalysts. Osmium is really toxic. Most of the heavy metals that we have to deal with are toxic. So if we can use them in small amounts, let's do so. So what people have developed over the years have been cycles and ways of getting rid of the need for a complete equivalent of this stuff. So what happens is the osmium gets involved with one molecule of the alkene, and then this guy gets involved, okay? Or this one down here, peroxide. And these extra pieces here are simply to reoxidize OS6 back to OS8. So I'm going to end up over here with OS at a +6 oxidation state. And if I want to recycle that, I need to oxidize it. So what we add instead as well is one of these oxidants, and that takes it back to the beginning to become osmium 8. So the conditions you will see, these types of things, N-morpholine oxide, don't worry about it just yet. 2-butyl peroxide, don't worry about the names just yet, that will come next year. Right now they're added materials to oxidize the osmium back, so you don't have to use a full equivalent to the osmium. Well, what I want to try and point out now as we head into the second term is that if you get this stuff, if it starts to make sense, the second semester becomes quite enjoyable because we head towards the biology, the chemical engineering ideas, by using the same principles, by applying what you know to new systems that you haven't seen before. So down here, potassium permanganate. You've probably used this at some point in the lab. What color is potassium permanganate? It's a heavy metal. Think of heavy metal bands. Come on, Joe. What color is it? Deep purple. It's deep purple. This thing looks an awful lot like the osmium above it. This thing, how do you catalog these things? Look at that osmium right there. OSO4. Central atom, very electron poor, wants electron density. Look at this guy down here. Permanganate. Almost exactly the same thing. You have a central atom which is very electron poor, wants some electrons back. Why is the structure different? Well, it's in a different group in the periodic table. So you have a different number of electrons, but it's doing the same thing. And you will pick that up if you want to do well at this stuff. The commonality is if that reagent looks a lot like the other one, it'll do very similar things. Why wouldn't it? Has the same idea, same sort of needs. So potassium permanganate also does this, and we end up, after an aqueous workup or a base workup, we end up with a cis diol. So now you have two ways of doing this, one with osmium and one with potassium permanganate. Now, if we were to count up, of the 125 reactions that you need to know for these two terms, I don't know, what are we at, 40? We're not that far in yet. So just keep up, keep a track, ask questions, stay awake in class, and see how we do. Okay, examples, then we're done for the day, and we'll come back and finish this on Wednesday. Between now and quiz, between now and exam coming up in the third week of November, this should mean something to you. This is a peroxyacid. This is going to deliver the extra oxygen to the double bond, and it's going to give us the epoxide. So the outcome here, after the hydrolysis in the second step, is the diol. How do you know it's a diol? Well, you learn the mechanisms, and you recognize that, first of all, you get an epoxide, then that opens up in a trans fashion, and that gives you the anti-outcome. How many stereocenters in that molecule? 2. Can I use squiggles? No, don't squiggle. You don't get all 4 of them. Next one down. We're adding here peroxyacid, we're adding to an alkene, we should make an epoxide in the first instance, and then we do an acidic workup or an acidic reaction. Am I going to end up with an OH here? Well, they're both going to go there, aren't they? You're going to end up with that. Okay? Again, it's the stereochemical issue here. They're both anti-outcomes. You don't get the syn outcome under any circumstances. KMNO4, you don't see much of this term. You see it next term a little bit. This is the only chance you'll see it here. Same reaction, basically. KMNO4 does the same thing as OSO4. They are very much complementary, and that should give you a diol. In this case, it's going to be syn because of the fact that this is adding in a concerted fashion. Joe?
How have something you know, OH groups, you're drawing like transistor states, you're thinking about transistor states, the like the nucleophile should attack the more, if the the nucleophile will attack the more delta positive carbon.
Yes. 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 Now, these are fairly straightforward. We will do labeling later. We will be able to trace some of these things next term when we do some labeling experiments, but right now, these are factual. This is what happens. So I'm going to mention this now, then we're going to take a time out. You're going to go home and wake up, drink some coffee, whatever's legal to wake you up, and come back on Wednesday for the second most loved reaction in the whole of the 2 semesters, ozonolysis. And I want to finish this off by just sort of making sure we're on top of this stuff. What does that word remind you of? No, not the one on the left, the one on the right. Breaking. Where have we seen that before? Biology, right? Lysing cells, opening cells, right? So chemists call it ozonolysis. You would call it, biologists would call it lysis. It's exactly the same process. We're going to break things apart. This is tricky. This is very tricky, right? There's an awful lot happening here in that ozonolysis process, and it's one of the more demanding things you need to look at. Okay, let me finish.